In this lesson, we are going to discuss electromagnetic waves. At the end of this video lesson, you should be able to differentiate electromagnetic waves from mechanical waves and describe the electromagnetic spectrum using the wave equation. We live in a world full of waves. When we say something is wavy, that thing forms smooth curves in and out just like what we are seeing from this animation. In the physical aspect, a wave is any disturbance that is propagated from one place to another in a regular and organized way. This can be depicted as vibrations from the equilibrium or normal state of a matter. These vibrations are displacements which happen both horizontally and vertically. Its highest displacement is the crest, and its lowest displacement is the trough. The crest and the trough give us the height of the wave regardless of its orientation. This is called the amplitude. The distance between two successive points, regardless if it is from two crests, or from two troughs, or even from two identical points of the wave, is called the wavelength. A wave is also a combination of the cycles of disturbances. These segments mark one complete cycle of the wave. This next segment shows another cycle. These cycles are recorded per unit of time as indicated by the wave's frequency. If these borders mark each second of a wave, this means that the wave has one cycle per second. And just like any moving object, a wave has a displacement per unit time as indicated by its velocity. The following wave variables are related to each other and are described by the wave equation. According to the wave equation, the velocity of the wave, which is measured in meters per second, is the product of the wave's wavelength, which is denoted by the small Greek letter lambda and is measured in meters, and the wave's frequency, which is denoted by f and is measured by the number of cycles per second or hertz. Waves vary in frequency, velocity, and wavelength. One primary reason for this is their medium for propagation. For example, a stone dropped on water will cause a disturbance as seen in ripples. Wind pushes ocean water to create ocean waves. These first two examples show the requirement of a liquid material for the wave to occur. Now let's look at the strumming of a string instrument. If we can look closely to the strings, the fingers would cause disturbance to the string through the vibrations. This is an example of a wave which requires a solid material for it to occur. This creates sound, which is also an example of a wave. All of these waves are called mechanical waves. There is a physical disturbance which creates waves that pass through a medium and have a velocity relative to the density of the medium. For example, sound waves can pass through solids, liquids, and gases, but they can pass through solids faster because of the closely packed atoms in a solid material. These waves can still pass through gases because gases contain atoms, which act as a medium for propagation. It is not possible for these waves to occur in a vacuum because there is no matter in a vacuum. However, there is another type of wave which can pass through vacuums. Suppose we have a static electric charge that would create an electric field. This will modify the electrical properties of the space around it, and this would be different if it is not here. If we allow this electric charge to move, its electric field is also changed. Aside from this, it will be creating a field in space in which force is exerted on magnetic materials. Take note that the magnetic field is only created when the charge is in motion. The magnetic field disturbance, denoted by the red B vector, is created perpendicularly by the moving charge, which also creates a moving electric field disturbance, denoted by the blue E vector. These disturbances create a combination of waves which we call the electromagnetic waves. These disturbances can occur in the vacuum in space. Thus, these do not require a medium for propagation. It is important to take note that although these do not require any medium for propagation, they can still travel through different states of matter. Also, in a vacuum, these waves will travel in the speed of light of 3 × 10⁸ meters per second, which is denoted by the symbol c. Electromagnetic waves vary in types and functions depending on its wave characteristics. To better understand and visualize the characteristics of the electromagnetic waves, we are going to focus first on their wavelengths. Radio waves have wavelengths ranging from 1 meter to 10,000 meters. These waves have on the average wavelengths as large as football fields. Next, we have microwaves. Microwaves range from as large as 1 meter up to 0.1 millimeters. On the average, microwaves may have a wavelength about the size of a baseball. Next are infrared rays. Infrared rays have wavelengths ranging from 700 nanometers up to 1 millimeter. It can be visualized as the diameter of a strand of human hair. Visible light, or the visible spectrum, ranges from about 400 nanometers up to about 700 nanometers. Its wavelength can be visualized as the size of soap bubble membranes and protozoans. Shorter than the visible light is the ultraviolet. It ranges from 0.6 nanometers up to 400 nanometers, or the size of rhinoviruses or the common cold virus. Shorter than the ultraviolet rays are the X-rays or the Röntgen rays. This range from 1 picometer up to 10,000 picometers. It is comparable to the diameter of the atom. And lastly, the shortest of all electromagnetic waves are the gamma rays. This range from 0.01 picometers up to 100 picometers. Their wavelength is relative to the size of the nucleus of an atom. Let us now try to identify the frequencies of the electromagnetic waves, which were discussed using their wavelengths. We have previously discussed in the lesson the wave equation, which is given by this formula. To solve for the wave's frequency, we are going to divide both sides of the equation by lambda. Thus, we have f is equal to v over lambda. Since the wave velocity is in meters per second and that the wavelength is in meters, the frequency is in 1 cycle per second or hertz. In this case, we are going to solve for the electromagnetic wave's frequencies in a vacuum. Therefore, the speed of the wave is the same with the speed of light, which is 3 times 10 raised to 8 meters per second. Thus, for radio waves, its frequency is 3 times 10 raised to 8 hertz. For microwave, its frequency is 3 times 10 raised to 12 hertz. For infrared, its frequency is 4.29 times 10 raised to 14 hertz. And for the rest of the waves, we have the following frequencies. From this data, we can see that the electromagnetic wavelength increases from gamma rays going to the radio waves, and that the frequency increases from radio waves up to the gamma rays. These relationships of the electromagnetic waves describe how the electromagnetic spectrum is arranged. The electromagnetic spectrum shows the increasing frequencies and decreasing wavelengths from the radio waves up to the gamma rays. These waves are emitted by accelerating electric charges and do not require any medium for propagation. To easily remember the arrangement of these waves, we may make use of this mnemonic device. Raoul's mother is visiting Uncle Sander's garden. The first letters in each word in the statement represent the different components of the electromagnetic spectrum in increasing frequency. The electromagnetic spectrum ranges from the size of football fields and may be as small as the nucleus of the atom, all of which we cannot see with the naked eye. However, in the middle of the spectrum lies the visible spectrum, which gives us the different colors of light. We commonly know this as the Roy-G-Biv. These colors comprise the rainbow. But have you ever wondered why the colors are arranged in such order? This is because each color has a unique wavelength and frequency. The red light, which has the longest wavelength and lowest frequency in the visible spectrum, is placed next to infrared in the electromagnetic spectrum. The violet light, which has the shortest wavelength and highest frequency in the visible spectrum, is just a step lower than the ultraviolet light in the electromagnetic spectrum. This may also serve as your guide in remembering the position of the components of the visible spectrum in the electromagnetic spectrum. Before the red light, we have infrared, which we can think of as the weaker red, and after violet comes the ultraviolet light, which we can think of as the stronger violet. And that is how we arrange the different components of the electromagnetic spectrum. To summarize this lesson, let us review the following key points. Electromagnetic waves are created by the electric and magnetic fields of a moving electric charge. The wave equation explains the inverse relationship between the frequency and wavelength of the electromagnetic waves. And lastly, radio waves have the longest wavelength and lowest frequency. Gamma rays have the shortest wavelength and the highest frequency. And that ends our discussion on electromagnetic waves.